Our new module is how predictive AI works on spreadsheet type data, not images yet, not sound or anything, or text. We're going to talk about logistic regression, and we're going to talk about deep learning. First, why should we even learn how predictive AI works in an age of generative AI? Well, for one thing, predictive AI is still an important tool in most STEM fields, and it's a stepping stone toward learning how generative AI works. So let's look at a medical testing context. Let's say we take a blood sample from a patient and measure how much of some chemical, we'll call it chemical X, is in the blood sample. And we want to say, based on their level of chemical X, do we think that this person has some specific disease, like heart disease or diabetes or something? We don't necessarily think that chemical X causes the disease, just that it's a biomarker related to the presence of the disease. The situation that we're using here with just one predictor variable, like how much chemical X, is not actually complicated enough to need fancy AI methods. The methods I'll be demonstrating predate AI by almost a century, but we can see this as a stepping stone toward the more complicated data sets and methods. So to have an idea of what values of chemical X might indicate that a person has this disease, we might collect data with permission from hospital records or from a bunch of volunteers about how their level of chemical X and whether or not they have the disease. We should ask questions about how these people were chosen, like were only people included if they already had at least one symptom of the disease, but we won't focus on that for now. I'll leave a link in the description for this data set. I generated the data artificially, so I know how it behaves, and partly because there's important privacy restrictions on getting real patient data. Also, real data is a lot messier than the data I'm going to show here, so we're just starting simple. I have a link here to the Julius notebook where I generated the data artificially. You can see which mistakes I made while I was generating it artificially. I'm going to do the initial exploration in a spreadsheet, partly because it's more clear what I'm doing with the data than when I'm using computer code, and partly because everyone in STEM should learn how to use spreadsheets, even if they aren't the best tool for many tasks. That's because a lot of companies use spreadsheets both for accounting stuff and for data analysis. You don't have to be repeating my steps yourself, though, but I'm happy to help to support it if you want to try. So let's take a look at the data here. There we go. So we've got 1,000 patients. I've listed a data type for each row, and it's all artificial. So being very clear about that, we would never want to accidentally confuse artificial data with real data. We have how much chemical X they have in their bloodstream, and we have whether they have this disease or not. So the first thing we should probably do is check that it has as many rows as we expect. I said it has 1,000. I said I would have 1,000, and we have 1,000. We should also see if there are any missing values. There are a lot of important statistical considerations when there are missing values, like why are they missing? Is that biased? I can use the count function to count how many cells in a range have numbers. So let's do that here. So I can say equals count. And I can click here and then hold Control Shift and press the down arrow, and that highlights all the data in that block of 1,000. Hit Enter, and I have 1,000 things. Let me just show that if I had a missing thing here, then that count drops. I'm going to hit undo and it goes back up. Of course, you should never change your actual data set. You should only change copies of it, right? If I try the same thing on this column, it tells me I have nothing because count only counts the numbers that are there. I would have to do count A, which is like count all. And that tells me I have 1,000 results there. So no missing data. That makes life easy, or easier at least. We should still ask, did a previous version of this data set have some rows with an empty cell, and those rows maybe got filtered out to make this data set? But we'll ignore that for now and move on because we know I generated this artificially. So we want to know how much the chemical X predicts whether a person has the disease or not. We might try to plot chemical amount on the horizontal axis and disease status on the y-axis, but the disease status is a word rather than a number, so it doesn't work. Let's go try that real quick. We'll go insert, um, and we could try a scatter plot, and we just get basically nothing. So we'll give up on that. So we need another way to plot what's going on. It could help us to look at what percent of people have the disease at each level of chemical X. So to do that, we'll use what's called a pivot table in Excel. This is a very important Excel feature, and a lot of companies will want you to know how to use it. You can look up tons of videos on YouTube about it for more practice and stuff, but you don't have to do that for this homework. AI doesn't typically use pivot tables. I'm just using them here to gloss over some more complicated issues. Happy to tell you about that at some point. I'm going to highlight the data block in the Excel spreadsheet. Um, to do that, I can just click in the data block and press Control A or Command A, and that highlights everything in that rectangle. And I'm going to go to Insert Pivot Table, um, and it says what range do you want the data to come from. I had already highlighted it, so it's got that. It's usually a good idea to put it in a new worksheet, so I'll hit OK. So it gives me kind of a blank table here and then some ways I can build the pivot table. So what I'm going to do first is I'm going to grab the chemical X field and put it in the row box. So click on this chemical X and drag it down here and drop it. And that puts it in the row box. And you can see it looked at the data set and saw all the unique values of chemical X and made a list of them in numeric or alphabetic order. And then I can take the has disease field and put it in the columns box. So we can grab has disease and put it in columns. And it looked at all the has disease entries, some no, some yes, put them here, but it hasn't counted anything yet. I can grab has disease and put it in the values. And then it tells us at 150 for chemical X, how many people did not have the disease, how many people did have the disease, and the grand total of people, that's actually a subtotal of people at chemical X value of 150. So that's the basics of doing a pivot table. Um, if chemical X hadn't been so rounded, then let's see, but then we wouldn't have had nice groups of them every 50. Like if we look back at the data, it's not reporting chemical X values of like 552.9 or something. It's all apparently rounded to the nearest 50. I did that just for pedagogical reasons. I'm happy to tell you what we would do in the more complicated case sometime later. If there had been blanks in the data, then we would have seen no, yes, and blank. We would have seen 150, 200, 250, 300, etc., and then maybe a blank row, a row for blanks at the bottom. So that would be another way to think about whether there are blanks in the data set. So now we can compute the percent of patients at each level of chemical X who have the disease. I'm going to do that over here. So we can say chemical X value and percent of patients who have the disease. So here I can say equals A5 to just copy the value that's currently in A5. And the percent of patients that have the disease would be C5. That's how many people said have a yes for the disease, divided by D5, the subtotal in that row. That's showing as a decimal between 0 and 1. I can come up here to the Home tab, the number section, and I can press the percent and maybe show an extra. So it's still treating it as a decimal internally, but it's showing it as a percent. I don't have to type times 100 into a formula. It's usually, we don't want to type times 100 into a formula. And then I can copy these and highlight this whole region and hit paste. Oh, let's try it again. And so I get a little table of at each chemical X value, what percent of people have the disease. So now I'll highlight the data and insert a scatter plot. So highlight the data, insert scatter plot, and we'll just use dots here. Let's check that this makes sense. The x-axis values seem to be reasonable for chemical X. Y-axis values are percents, so that's nice. I can put some axis labels on it. That's probably a good idea. So I can click here, say equals, and that. And then we can ask, do we see a predictive relationship between chemical X and the percent of patients who have the disease? Think about that. Well, you might say that we see an increasing trend, right? The more chemical X someone has, the higher the percent of people with that chemical X who have the disease. We could try adding a trend line. So I can right click on a data point and say add trend line. And it's often nice to say display equation and display R squared. We'll talk more about R squared later. So this quantifies that. So we could say at a chemical level of 600, for example, I could put 600 in here for X and get some value that's probably near 50 some percent. And that would give us an idea of how common it is to have this disease at this chemical level. Um, so do you see anything interesting or worrisome about this trend line? Think about that. Well, if we kept following it, at some point it would go above 100%, and you can't have a percent of patients that's above 100%. Similarly, if we kept following it off to the left, it would go below zero. In fact, it does go below zero, even on the graph here, and you can't have a percent of patients that's below zero. So we would hopefully find a better sort of trend line to use than this straight line. Um, so and any straight line, any slanted straight line will eventually go above 100 and eventually go below zero, going back the other way. So we just need something other than a straight line.